Hello, fellow engineers. Welcome to Coding with Alexor. Today we'll be implementing the heap data structure in Rust. Before that, let's review what's a heap on our whiteboard. Yeah, when we're talking about a heap, actually in nature, there are two types. It's a MinHeap and a Max Heap. So we have a binary tree structure, which needs to be a complete binary tree. So important thing to notice is the fact that, for example, each parent, so let's assume we are at this level, we need to make sure that both children, the left and the right children, are less than the parent. So that will represent a MinHeap. For a Max Heap, it will be vice versa. Pretty much the parent needs to be bigger than both children. So this applies for pretty much each node of the heap, and this will make sure that our heap is properly ordered, min or max heap. Throughout today's code and challenge, I'll be using mainly max heap. So first, let's try to represent it in a vector data structure. So for that, we'll define 7 boxes. Why 7 boxes? There is a trick for that. Usually for all binary trees, you'll need to find out the height of the tree. Then the maximum number of elements in a height will be the following formula. It will be 2h minus 1. And in our case, we have h3 because we have 3 levels. So we have 7 elements maximum. So let's draw 7 boxes. Will be nice if we order them. So for example, in the literature, you'll see them ordered in the form of the first, second, third, fourth, fifth, sixth, and seventh. Though it will be a little bit trickier when we need to implement the code, and I'll show you why exactly. So let's add all those nodes and represent them in our vector. So for example, 60 will go at the position 1, 30 and 25 will go subsequently position 2 and 3. Next, we'll do 15 and 10, 15 and 10, and last part will be 20 and 15. So actually, it's a hack on how we can read, let's say, a heap data structure. So you can go 60, then this way, then this way, then this way, and this way. So pretty much, if you read it like that, this will be exactly the representation in our vector. Out of this information, we kind of need to draw out what's the parent and what are the nodes, the left node, the right nodes. For example, how we can fastly find who's the parent of element at the position 7, 15. So there is a formula for that. So usually it's 7 divided by 2 or index divided by 2. And for that, it will be 4. So it will be 25, it will be 3. So this one. Yeah, this will be the parent. Or actually, we can go the other way around. So we have left, we have the right one. For this one will be, let me change the color. So this will be position 4 and position 5. So right and left one. So if you go at the 25th one, so element of this position 3, it will be this, the right, and this will be the left. So that's actually a representation of tree in a vector form. Although this, we'll need to implement a couple of functions. So let's get back to our coding board. Okay, so to save a little bit of time, I've decided to change the approach and write the code ahead. So here mainly what we'll be doing, I'll be explaining the existing code. So first thing which we'll need to do, it's just to implement, to create a heap structure. So we'll have the following one. Yeah, let me collapse everything. So we'll have a publicly defined heap. Also important for us to have a data. I specifically used here a vector of I32. This is not necessarily to do it like that. And as an improvement, what we can do further is just to make sure we're using generic. So instead of using I32, we can specify here a generic and implement it for pretty much all possible data structure, which are comparable and copyable, I guess. So this is what we'll need to provide. But for the sake of, let's say, going faster and moving forward, let's use just I32 type, because we'll implement it specifically for I32. So the following things we'll need to implement. So first thing, this is the new function. So this is a common pattern for, let's say, implementing things inside the structure. In our case, we have a new. So if we're looking exactly, it's nothing else. We just define an empty heap. We have an empty vector for that. The first function, important function for us to look at, will be, let's say, insert an element into a heap and then popping an element from a heap. Why popping? Usually you can find it called as well as removed or deleted. But it's popping because pretty much we are removing an element from the root. So every time it will be the root element. It's not possible to, actually it's possible, but let's say the default heap implementation just supports popping the element from the root. As well, we'll do a heap sort. So this is, let's say, the coolness of a heap data structure. Let's say the pinnacle of it, it's the heap sort algorithm implementation, because it's pretty cool. What else do we have? We have the parents, how to get the parent index, how to get the left index, the right index, a very important function called Heapify, where we'll be explaining it briefly at the whiteboard, and then some helper function used in the Heapify one. So let's start first with inserting an element in our data structure. Always what we do, we start with adding a failing test. So let's imagine we didn't write any code. We added our failing test. So in our case, it will be, we'll be inserting an element at the non-empty heap. So we need to generate a heap, which is a max heap in our case. And we need to insert the element 60. The algorithm for implementing it, we can outline on the whiteboard, though I will not do that because pretty much there is the internet is full of how exactly it's done. But we'll be looking at the implementation in Rust and you'll totally understand it. So from the code part, you'll understand how this is working. So the end result will be 60 being the root element, because we can see right away that 60 is the biggest one, so it should go as the root element. We have, let's say, the expected output to be 60, 50, 20, 35, 10, 8, 6, and 15 for the given input. So let's see the implementation of this part. First thing which we are doing, or we intend to do, it's push the element in our vector. So the element will be the last one. Then we'll be getting the index of that element, because pretty much what we'll need to do, we'll need to find the parent of the last element and then compare if our element is bigger than the parent. If it's bigger, then we'll need to swap it. So we'll be doing this till the moment where pretty much all parents were consumed. So that's it. Behind the scenes, it will be just traversal from bottom up, and everywhere where the parent is smaller than the current element, we'll be swapping it. That's it with the insert part. Let's move further. So we can give it a try. We can run our test. So our test is successful. Let's collapse it and move further. So with the deleting of the element. In our case, the pop function what's expected to work, or how it's expected to work. So first thing which we'll need to do is define our inputs. So we'll have a heap. It will be the same heap used previously. And now when we're calling heap up, we'll need to return a sum. So usually it's a good way on to return an option instead of just returning the value, because it's possible to call, let's say, pop on an empty heap, and then it will just panic, and it will be an exception in Rust. So in this case, we're returning an option, so it will be either sum or none, if, for example, it's an empty heap. So we are doing two asserts here. So first assert will be that the element will be 50. It's a sum of 50. And we are checking the data inside to pretty much be removed. We don't expect anymore to have it the element at the position 0, 50 in our heap. So a little bit of reordering is done. This procedure is also described, the algorithm is described on the internet. So I'll just provide a YouTube link or a lecture with the implementation. So we'll just be focusing on analyzing the code. So here what I am doing, I'm using the match pattern. So because sometimes we're getting into different bounds issues. So for example, if the size of the data is 0 or 1, in these cases, we are just, we don't need to do pretty much anything specific. What we'll need to do is just to pop it out. So for example, for 0, we'll return a none, because we cannot pop anything out of our data. For 1, we'll getting the element. So as pop, it's an array. So we'll just, or a vector, will return as an option. So we'll not even need to change. So for all the other cases, we have a little bit different implementation. So here as well, we find the last element. And the tricky part here, when we do a pop, the element, the last element will become the root element, and we'll apply a function called Heapify. So this is the important function which I mentioned. So Heapify, the algorithm will be looking at it right in a moment, but for now, let's see the, let's say, high-level view. So we are getting the data, so we are returning the data or our value. So yeah, we're doing the swap element at the position 0 with the last element index. We are popping the last element, and suddenly after the swap, this will be the root element. We're sorting the value, so we'll be returning our value. So let's get into Heapify function. So the Heapify algorithm pretty much does the following thing. So what we'll need to do is kind of, once we have the root, so imagine the root element is at the position 0, we did the swap part, and now we'll need to traverse and check everywhere to make sure that let's say our heap supports, let's say, the heap rule which I outlined on the whiteboard. So how I do this stuff? So we'll need to find the left children and the right children. I'll define the size. So for example, if left is bigger than the size, so this is just a check for out of the bounds issues, because if we're looking at the left and the right function implementation, it's on the following form. So let me open it up. So pretty much left will be 2 multiplied by index plus 1. And the right one will be 2 multiplied by index plus 2. So that will be the formula to find out the left and the right children. And for parent, because we also are using parent, is index divided by 2. So what do we have here? We check the bounds. If left and right are in our bounds in the size, then we continue our code. If not, if they are bigger, then we break. Next thing what we do, we will need to find out which one is the biggest out of, let's say, parent, left children and right children. So I've used this function for that. So pretty much we're checking, comparing all elements like a left index, right index, and the current, which will be kind of parent in our case. So if, for example, we found out the max, it's the left, or if the max is the current or the parent, we're returning index of the current. If it's the right one, then the right index. So the left index will be the default one in this case. So just a helper function to make the algorithm clearer to read. So nothing fancy here as well. So again, we are traversing from top down, and we are comparing again for the parents to be, if it's a max heap, as it is in our case, for the parents to be bigger than both children. So if we found out some problem with that, once we found out, let's say, the max element, if it's not a current, because if, for example, it happens that the max out of 3 it's the current, then we don't need to do anything. We just break the loop because we have already a max heap. If not, we'll change the current with the max element out of the 3 ones. Okay, so we'll mark the current to be the max one. If, for example, we did a swap because we need to go recursively. It's not a recursive implementation, though it's totally possible to do a recursive one. So that's the Heapify function. If we do try to run our test, we'll see this one works as well. Awesome. So we did implement it properly. Next thing what we'll do, okay, so yeah, we'll need to make sure that we did implement the possibility to create a vector from, I guess, to create a heap from a vector. So for that, let me collapse this one, unwrap this one. So for example, we have the following vector. I've added a trick, actually not a trick, but let's say usually how it's implemented in Rust, you need to, you have a from trade, so you can specify the type, so you can have, let's say you can create heaps from different types, but you'll need to implement for each type separately. Here we use heap from vector and we compare the data to have the right result. There are multiple ways on how we can implement it. Either we can go with this implementation, which I used specifically. So we have our, let's say, vector as a data. So first thing which we do, we just assign our vector to our heap. And then backwards, for each element backwards, we just apply the Heapify function. Because if we remember how Heapify works, it will go downwards and it will try to make sure that the property of a max Heapify or min Heapify is satisfied. That's one way. The other way around can be an implementation like inserting in an empty heap. It's pretty much the same logic. The algorithms both are, let's say, n log n for the complexity. So it just stays. You choose what you want. The other one can be the following, like we can have 4 element in data. So we can do heap insert element. So that as well can work. So pretty much we'll be calling the insert function from our heap. It will be the same time complexity. Okay. What else do we have? So yeah, we have our dessert here. So for dessert, we left the heap sort implementation. So heap sort it's a pretty cool way on how, let's say, you can acknowledge the heap data structure. So in our case, we are providing a data for our test case. We call into sorted vector, and we'll be returning back a sorted vector. Let's see the implementation of that. So let's get to into sorted vector. So you'll see how cool it's the implementation. So pretty much we'll define a vector, then we'll be popping out till we have data in our array, and at the end we'll be reversing our array to have it, let's say, sorted in ascending form. So yeah, pretty much every time when you call pop in a heap, if it's a max heap, then automatically it will be the biggest element remaining in the heap, so it's automatically sorted. So that's a very cool feature of, let's say, a heap data structure, and you can use it as a sorting algorithm. So to compare a little bit the time and space, where, for example, time, sorting or heap sort, it's n log n. It will be big of n log n. Though quick sort, some implementation of quick sort still can be faster. Even if, let's say, worst case scenario for both will be big O of n log n. I think that's it with the implementation. Now we can expand pretty much everything and see the whole structure and code. I'm planning to push this code into a Git repository, so if anyone can look at it, find out, maybe do some suggestion, or implement yourself. Maybe add this generic approach where we can have it there already. Though I will not suggest to do that, because pretty much the whole thing which we did here, it's just for us to understand how things are working. In Rust, there is already a binary heap data structure. So you can find it from BinaryHeap. So it's from content collection. Yeah, probably I'll need to call it in a function, and then I'll be able to call it. So we'll have a BinaryHeap. So yeah, binary heaps, you can find it from std collection, where we can have hash maps, hash sets, and pretty much very useful stuff. So we don't need to implement it right away. It was interesting for me to look as well how Rust guys implemented it. Though I saw that they try some unsafe stuff, probably to make it super fast. So I'm pretty sure that this implementation will be much faster than mine. So probably no sense on, let's say, creating a crate and publishing this as a crate. So yeah, you can open and see the whole implementation, but overall the same principle, like appending stuff, let's say popping stuff. So stuff remains the same. They use a generic type, which I think it's a thing which we can do. Yeah, probably we miss to implement the peak one. Peak function will enable us to tell if there is an element, the position, in our case the position 0, if we have anything in our queue. Though I guess we'll leave it for the next challenge. So hope you enjoy this. So if you like, please press the like button and subscribe. Every week on Sundays I'll be posting a coding challenge.